All right, and so now, right after viewers and students of mine have learned about how to find maximum and minimum value problems, then usually I would start teaching about how second derivatives can also be useful quite sometimes in your work of finding maximum and minimum value problem. So in my earlier video lessons, I have shown how we can use a first derivative test. And so now I am going to show some, I'm going to head into what can be useful about the second derivative, and I'll make my way to connect that into the finding maximum and minimum value problems. And so you can find out how useful a second derivative can also be used to find a maximum and minimum value problem. Okay, so here I would like to look a little further in depth about second derivative of any function. Second derivative, and now specifically we want to look at it's called the second derivative test. All right, so that's what we're heading into for this particular discussion. Okay, so now I am going to step to the other board and let's have some quick look back at any graphs. So I don't need a computer to draw the graphs, but now let's say you are given the graph of a function, any function. It has up and down and up and down. Okay, x-axis is here, y-axis is here. Our graph has ups and down, and so you have learned already in your lessons about how to find a maximum, minimum. These peaks right here, we have already found how first derivative can explain a lot of these. So, but now I want everybody to have even a closer look, okay, in terms of those peaks right here. But this is how I see it. Believe me or not, but any graph doesn't have to be this graph. It could be a nice parabolic graph, or it could be a hyperbola, or like whatever shape it is, e to the x logarithms. But any of your graph is a combination. Any of your graph of a function is a combination of these four fundamental pieces right here. You see right here you have an increasing piece of the graph right there. Okay, but now talking about the shape, this thing has that fundamental. So when your function is increasing, there can be one fundamental increasing shape. So now I'm talking about not increasing as a direction, but now increasing as a shape. Then your graph can be increasing in a bent down way like this, and which is what's happening right here in about. And I'm only making a rough estimate, but in about that interval, then we have our function increasing in a bending down shape like this. Okay, and further, when a function is increasing, okay, the function can also increasing in a way where in a shape that's bent up like that. Okay, so increasing. First derivative can explain about increasing, but increasing also differs about whether it's increasing as a bent down shape or it's increasing as a bent up shape like this. And so in a graph I'm drawing like this, see, there's this portion that I can recognize. See, it's increasing. Your function is increasing, but look at the shape it is. It's bent up. And so now I'm using that term bend up or bend down, but see, think about it came out from part of a cup right there. Either you have a cup that's holding water like this, or a cup that's upside down that's spilling water away. So this is bent up and this is bending down right there. Okay, and so back to what I was in the middle of saying then. Just about recognizing your function is an increasing function or being increasing in a certain interval, then there are two different ways of increasing. It could be increasing in the bent down shape, or it could be increasing in the bent up shape like that, like this right here. And so alternatively, or actually on another hand, so now in some area where your function is decreasing, their decreasing can also be, your function can also be decreasing in the bent up shape. And if it's a bent up shape right here decreasing, then the shape is going to look like this. Okay, it's bent up because it's part of an upholding water cup right there. Okay, that's why it's called, it's bent up. And then same idea, when your function is decreasing, it could also, your function can also decrease, decreasing in a bent down shape like that. Okay, so for up to this point, I have introduced 4 fundamental shapes right there. So, and those are, believe it or not, those are the only 4 fundamental shapes ever, but just simply a combination of those shapes makes up your graph. So say, for example, in your graph right here, I can see that there's about an interval between here and here. It's decreasing, but this is, see, bent down shape. And between, in this small piece of the graph, it's decreasing still, but it's bending up. Okay? So now, bending up and bending down, that's the concept of concavity. Okay, so now let me head back to the other board right there. So now, when your function is increasing, like that, right? And just like how I was drawing earlier, and the function is increasing in the bent down shape like this, formally speaking, now this is, so this shape right here concaves down. Okay, concaves down, but increasing. So now concaves down is when your second derivative must be negative in the interval, and of course the function is increasing, so your f prime, your first derivative, is a positive. Okay, and so that's one fundamental shape. But how about I'm going to use the dotted straight arrow over here, because we're not really looking at the f prime. We're looking at yes, it's increasing because it's, but bends down or concave down. So that's where we're looking. Your second derivative of the function must be negative. Okay, and so same way. So now when your function is still an increasing function, from the left to the right, getting higher. That's why my arrow is like that. But if the function is actually increasing in a bent up shape like this, so we refer to this as this situation right here, we call that the function concaves. Okay, function concaves up. Okay, because see, I was explaining earlier, this piece of the graph, imagine that it came out from an up, pointing up cup right here that's holding water. So if water in here, it's holding water. So in that way, so increasing, see the way how I'm drawing my arrow, and from the left to the right, even this shape right here, if you're looking from the left to the right, it does get higher. So increasing, it makes sense that your derivative is still positive in this case. Okay, your first derivative, but now your second derivative, to be to indicate concaves up, your second derivative in this case must be positive. Okay, unlike the other case right here. So in this case, the derivative is positive. Okay, and first derivative is positive, but second derivative is negative. So it consequently turns the graph as a concave down graph. And now on the other hand, the other two shapes, when your function is decreasing, okay, when your function is decreasing, then it can decrease in the bending down shape like this. So this decreasing means your f double prime. Okay, your f double prime, your f prime of x is negative, but your f double prime here is also negative. Okay, so generally speaking, these two cases, I put them in a column. Now putting it all together, and if we're seeing that as a table, then these two cases here refer to all about the function concaves down. Okay, and now so just like that, when your function is decreasing, meaning f prime is negative, but the function can also decrease. F prime is negative. Okay, but your function can decrease in the bent up way, and bending up way means it has to be in a primary, in a fundamental shape like that. It's falling down but bent up. Think about, imagine that it came out from an up, holding up cup like this. Okay, the cup that's holding water, and the cup here is spilling water. See, this piece right here came out from that half portion, and this other piece here came out from that other half of the upside down cup. So that's why it's concave down, and here this is concave. Concave upward. And so second derivative has to be positive in this case. All right. And so now these are the four fundamental shapes. So if we're looking at the whole thing here as a table, then the two first cases here in the top row, that's all when you're looking at increasing. Okay? And then the two cases in the bottom row here of this table, and now we can see that as the cases as decreasing. Okay, so that explains about the, so again, that's how second derivative explains about the shapes of your graph once you already knew whether it's increasing or decreasing. And so blended together with our understanding of first derivative, then it came to these four fundamental shapes here. Okay, and so now there will be back on a graph like this. So if you're looking at even a little closer, if you're looking at the graph here a little closer, and if I just say simply extract out this little segment of the graph right here, so it has a concave down piece here. And then all of a sudden it's hard to tell where exactly that is, but because the changes is so, I mean, it's not a sudden change. It changed so gradually, but eventually it changed that we're so unaware of that. Okay, but there has to be a point somewhere on the graph here where, see, if we pick a point here, you can see that there has to be a certain interval where your graph was concaving down right here. And all of a sudden, we couldn't realize where exactly that point was, but the graph eventually turned into a point concaving up. Okay? And so in one interval like this, the function was decreasing, but it changed the concavity twice. I mean, it had a change in concavity. It changed from concaving down to concaving up, like that. And so the point, so there has to be a point somewhere, that point in particular. So now I'm trying to draw an arrow that points to that point where the function switched in concavity. And that point there we refer to as inflection. So maybe let me write it in red ink because it's a good terminology to know. So that point where we notice the changing in concavity, switching in concavity, we call that point the inflection point. Okay? And so now I have to call it, it's an inflection point, meaning it's a complete pair of values. So x, it has x and y, and x and y together, it makes itself stays on the graph right here. So x on the x-axis, and wherever y that is. You see what I'm saying now? Okay, and so now once I turn out that understanding right there, then see, you got quite a few other inflection point here. There's another inflection point right here, because it seems like our graph here in this interval changed from concaving up, right, to another piece that is being concaving down. The function was entirely increasing in that interval here, but you can see that it was concaving up. Then there was some magical point right there. We call it the inflection point. The function changed to concaving down right there. And so that's how we call them. These are the inflection points right here, or in plural, those are the inflection points. Okay, and so now, just how I have explained earlier through the little table, then anyone viewing my video has already had a good formulation, but let me just write it down in formal worded description right here. So this table is perfectly good enough already. So now let me write down a formal description right here. But this is what we formulate through investigating graphs right here. I shouldn't say formulate, but let's call that, let's say this is in general. Okay, so generally, this is what we found right here. So the function f of x, okay, the function f of x will concave or just concaves down, right, on any interval in general if its second derivative f double prime is negative. So that understanding right here we formulated by looking at this table right here. F double prime is negative. F double prime is negative. Our function concaves down right here. See, bent down. That's where second derivative is negative. And so same way, similarly, the function f of x will, okay, in another case here, or concaves up, right? If f double prime is positive. Okay, so just like that here, when it's, see, look a little more closely on the table I've had on the other board, just right here. Then these are the two cases for concaves up, and as I have explained earlier, this is where f double prime is positive. So putting that in a worded description, then that's how it is. The function will concave up, right, if f double prime is a positive value. And so now, in my explanation earlier, think about we got a concave up, and then it switched to concave down right here. So that point right here, okay, that point, this is where we call that the inflection point, but now this is where f double prime, I mean, maybe on the x-axis, maybe it's some value x equals c, for example. And so let me now say it clearly. F double prime at that particular instance right here, where we have that small value where it's, I mean, that particular instance where it switched from one concavity to another one, that's referred to as, I mean, that is when f double prime equals 0. Okay, so this is not the only case. It could be something like this, switching from a concave down, okay, and switch to a concave up right here. That point right there, that's another case. Okay, and so could be in another quick little graphic there. We got our x equals a right there, and that's where x equals c, I mean, okay, and that's where our f double prime has to be equal to 0. And so I couldn't put that on my table from earlier. So now, but now we can put in a generality here among my worded description here. So the function f of x, okay, has an inflection point. Okay, in inflection. Right, inflection point. Right, and then that's simply happening at x equals c if f double prime at c, okay, equals 0. Okay, so now we have a generalized formulation of how second derivative explains about the shapes of our graph. And so now, how does that explain about finding maximum or minimum value? How does that explain about finding maximum or minimum value? So allow me now to erase this board of mine, because just like what I was saying in the beginning of this particular video lesson here, then I would like to show more details about second derivative. And just now we've learned it, but now how can that be applied into what we learned most recently here, finding maximum and minimum value problem? And so now I have to be clear, this is the method that's particularly once it works. If the second derivative exists for any function, then it's the best, I mean, it can be used quite effectively to find local maximum or minimum values like that, or local extrema. Okay, but only for local extrema. It has nothing to do with absolute extrema, because always we have to find local extrema first before we can decide among the candidates, right? Who's the absolute maximum and who's the absolute minimum. So what matters the most is how we can use a second derivative to decide the local maximum or local minimum. But now, before I really get into that, let me bring up a graph again. And the graph has low and high and low and high, just any whatever graph that is. So this point here, say everybody already knew that this bottom peak right here, tangent line, is horizontal. And so we call the x value right there, that value in particular, we refer to that as a critical value. We already learned that through the earlier lesson. So this is critical value. And so the function, I mean the derivative of the function at x equals c must be equal to 0 or undefined. But in the case I'm drawing my graph here, then I'm pretty sure it's equal to 0, not the undefined case, because it's not a sharp angle turn or anything like that. But now, what we just now learned about second derivative, think about it. I mean, the picture itself tells that this point has to be a minimum, right? Now, look, I just want anyone following with this lesson here to simply look at the picture right now. The picture shows a bottom peak. So showing a bottom peak here means, well, look at the shape right here. The shape's where this point belongs to. Look at the shape around this point. So this point is our critical point, our critical value right here. But look at the shape around that. It is entirely bending up shape, isn't it? Because that's the way it is. As long as your cup is bending up, then the peak has to be a bottom peak. Just the way just perfectly the way how the geometry happens out there. Okay, we are the mathematicians. We only try to explain what we're trying to recognize and discover what's going on, but that's just how it is. And so when your cup is pointing up, then that peak has to be the minimum peak right here. It has to be the minimum. So now that actually opens up a clue for us. Pointing up, the graph concaving up or pointing up means f double prime has to be positive. You see what I'm saying now? So now my intention here is that, you see, look at that point right there. Then now if you substitute that c into your f double prime, then to have a minimum, it has to be a positive because the cup is pointing up. Okay, and so right at that critical value, okay, then we having a minimum, we having a local minimum if the f double prime at that critical value is a positive one, because it's indicating that the point belongs to a concaving up cup right there. Okay, so on the other hand, what about this point? As far as tangent line, that tangent line is again horizontal, meaning that first derivative has already been known. Let's say I'm going to call that a different value, about x equals d, for example. Then f prime at d, we know for sure from previous lesson that this is 0 derivative at x equals d. Okay, but see, look at the shape of the graph around that point. So this point is another critical value right here, a critical point right there. Okay, but let's look at the shape of the graph right around it. At least there's some area around that graph locally. That's, the graph was pointing down right here. So that means what I recognize here is f double prime at d right here should be negative, okay, because the graph here was concaving down. See, and that's the way it is. Okay, when your cup is pointing down, then it can only have a highest peak, and that highest peak is now what we call the maximum. Okay, and so that's now we have a formulation, and we call this the second derivative test right here. So now for our work here, let's come up with another general formulation. And actually this is now good that we named that the second derivative test. Okay, and right after this I will be showing an example. Okay, so the second derivative test, I'm going to start out by saying, I'm going to say let x equals c be a critical value, okay? Critical value, and assuming that the function, the second derivative of our function at the critical value here exists or be defined, okay? So that's the first critical thing. So because there could be time the second derivative test fail, but that it fails because when we cannot have a second derivative, there could be time where we can only get the first derivative or at that point, but we will fail to find the second derivative at that same point. And so here, critically important that you got to understand that at your critical value, we must also ensure that we can have a second derivative at that value. And that's what I mean by f double prime at the critical value exists. Okay? But if that's so, if we already had that requirement satisfied, then here's the thing. Okay? Then if f double prime at c, okay, is a negative value, okay, then f of c, the function value at c, is a, now I call that a local maximum, okay? Or another way of saying we can get a local maximum at at x equals c in our function, okay? And that's one case right here. That's how we call that. It's the second derivative test. And on another hand, if the second derivative at our critical value is a positive value, then the function f of c, or the value of the function at f of c, is a local minimum. Okay, so we will have a local minimum and we will have a local maximum when it's this case. And that's how we come up with our what's so-called the second derivative test. Okay? All right, so now let's look into some example to see how we can apply that. And so this is in the end, it's a separate, because I'm not only intending to show how second derivative can be useful for finding our maximum or minimum, but I will also use this understanding to drive into another kind of application for second derivative. So second derivative has some good amount of applications as well. It can be used as a good way to determine your local maximum and minimum. But outside of that, there are other applications as well. And so that's why, this is a completely separate lecture right here compared with the other lecture, even though they are related. So now, let me now call that example 1 right here. So I am going to say find all local maximum and local minimum values, okay, of and here we are. Here's our function. How about f of x equals 1/3 x cubed minus x. So at this point, once I end the instruction of our example here, then anyone viewing my video lesson is feeling like I'm bringing back the old kind of problem. But no, I have my own intention. So here's what I'm doing. We want to be using, so my intention here is using second derivative test. Okay? Because without this indication, then anyone can just follow the methods we've learned in my earlier lessons, and we're going to be just fine to be able to find all the local maximum and all local minimum values. But here I intend to apply our second derivative test to find local maximum and local minimum. Okay, And so, and now, doesn't matter what test you're doing, first derivative or the second derivative test, but you always need to track down, because in the end, let me emphasize earlier, even if we have a what so-called second derivative test, but it still heavily depends on where your critical values are. So because the only way that local maximum and minimums happens, the only way that is that those local maximum and minimum values only happens within those critical values. So we always need to use to take our first derivative to find the critical values, and then we're gonna, and from there on we're gonna apply to the next step to decide who's the maximum and who's the minimum. And so my f prime here is going to be easily, we get, taking this derivative, the three multiplied together, what 1/3 cancel out, and now just give me x squared minus 1. Okay, and that means now I have my first derivative. So sooner or later we will find a second, we will use a second derivative test. So think about it as a planning ahead right here. It makes sense that we should go ahead and find a second derivative, even though that step is not there yet, okay? Even though we haven't used it yet, but let's go ahead, and since we're all working with derivatives, so let's find a derivative. So second derivative here is going to be 2x. So I'm going to keep that there for later use. But what we need right here is a f prime right there, because right now, once we've had f prime, I am going to use that to detect all of our critical values. Okay, so let me move on to the other board again. I'm going to spend some time erasing it. All right, so now, just like how we have done this before, I am going to set our derivative x squared minus 1 equal to 0. And what we plan to do, what we're about to do with this, we want to solve this equation here for x, because that's the only way how we can find critical values. And so this equation here on the left hand side, we can easily factor that down to x minus 1 in product with x plus 1. And that equals 0. And that means now we lead to two solutions. We're ending up with two solutions. X equals positive 1, and another one, x equals negative 1, that satisfy this equation. So now we have just now solved for our critical values. So now these are critical values. I put them in a box just to emphasize their importance. Okay, but that's not our final answers. Okay, so now here's how. So the idea now is that we don't need to use a sign chart to check for the, see, this is back in earlier lessons when I was using, if we were using first derivative test, then we would build a sign chart, and then there's negative 1 here and there's 1 here, and we check for the interval where f double prime is positive, whichever the interval here is positive, whichever the interval is negative, and that was the first derivative test, ladies and gentlemen. We are not going to do the sign chart here. We can bypass the sign chart. As soon as we got to the critical values, this is where the two tests go different paths right here. Okay, first derivative test, we built the sign chart, but second derivative test, this is how we're using it. Right at my first critical value 1 right here, I am going to substitute that into my f double prime. Okay, remember the writing I was putting down earlier, that at the critical value x equals 1, okay, if this derivative, so let's find out. The second derivative we found was 2, and now 2x, and now times, see, recall for yourself, f double prime of x is 2x. So now substituting x equals 1 into this, 2 times 1 equals 2. What matters for me is it's a positive value. So now conclusion say, that means f double prime at this critical value x equals 1 is a positive value. Now what can we say? Now, according to the second derivative test, back to what I was saying in about halfway earlier, now we can conclude that at this critical value, if the second derivative at that critical value is a positive, right, that means the graph points up. That means we have a local, see here, it's just a description. We have a local minimum. Okay, we have a local minimum at this value x equals 1. That's one thing I know for sure. So it tells us a plan we all have already detected and decided, instead of using sign charge, we already detected that at this critical value we know that we will have a local minimum due to the fact that the second derivative is positive at that value. Okay? But now we're still going to need to advance further and find our actual value. So the value itself there is going to be, now I'm going to substitute x equals 1 into the function. And we're going to calculate, and that gives me, so this is only for testing to decide if it's a maximum or a minimum. But now we're going to substitute the critical value back into the function to find the actual value, because we only find out where it happens. So it happens at x equals 1. But we didn't answer how high or how low it was. So now I'm going to substitute that in. And so with my function being originally 1/3 x cubed minus x, here 1/3 times 1 cubed minus 1 right here. So calculation comes out to be, right, so this is simple enough that I don't think I need to step away for the calculation. So negative 2 2/3. Okay, negative 2/3. All right, so that is my local minimum value at x equals 1. Okay, so we found one answer. Now, what about the other one? Because we found two critical values. This one here was a local minimum, and we already found the value. It hits down to as low as negative 2/3. I'm going to need to erase the board. And let's take care of the other critical value. So for the other critical value, negative 1, I am now going to substitute that into my f double prime. Okay, and so for f double prime, in this case here, my f double prime is 2x. Okay, so that means it's 2 times negative 1. Recall again, f double prime of x. We found it to be 2x from earlier. Okay, and so that's why now it's 2 times negative 1. And our final answer is easily negative 2. So the value is not important. The sign here is what's important. That means, according to our written second derivative test that I wrote down earlier, then the function, let's just write down the conclusion first. So what we observe here is that f double prime at this critical value is negative. That's what I see. That means now we are going to have, it leads to a conclusion that we must have a local maximum, okay, happening at this critical value x equals negative 1, due to the fact that, you see, your graph must be heading down like this, right around that value x equals negative 1. Okay, it's a peak having critical values indicating that we have horizontal tangent, but the graph around that is pointing down. So that's how we can now tell that it's a local maximum. And so now in that way, but that's just a decision that we've made. We made a decision. So now the actual calculation, I am going to substitute the critical value into my actual beginning function. So my original function says this is 1/3 times negative 1 all cubed minus negative 1. Okay, and so now this is going to be, okay, all that is 1, and so all that there is 1, and then subtract away a 1/3, so it's a positive 2/3 right here. This is my local maximum value happening at x equals negative 1 like that. Okay, so now concluding our answer. We already had our answer, but in case any of my students or any of your or any of our viewers here is having an instructor who want to see all your generalized conclusion, then this is how we say. Okay, so for local minimum, we have found f at 1. equals to negative 2/3. And that's happening at x equals 1. Okay. All right, that's our answer right here, and that's the only one for local minimum. As far as local maximum, then this is, we found the value as low as f of negative 1 being positive 2/3, and it's happening at x equals negative 1. That's the other answer, okay, in our example here. Okay, to find all local maximum and local minimum values of this designated function. And that's the whole idea about using the second derivative test. So like I said, the second derivative test doesn't always work, simply because in some problem the kind of function you are given might fail. You might fail to have second derivative at your critical value, and if that case happens, then you only have left with the first derivative. But if usually, in my experience, if the second derivative exists, then this is a much more effective tool right here to test for, to check for, whether we have a local maximum and local minimum. And further, I would like to say, this does not change the way how we find absolute maximum and absolute minimum. Because now let me put that, even though it's a separate lesson, but let me recall that again. Right, so now on my other board, when I was going over the lesson about specifically finding maximum and minimum value problems, then when it came to finding absolute maximum and absolute minimum, then this is how we did. So as a general step-by-step instruction for absolute maximum or the absolute minimum. Okay, it's the same instruction for all of them. But we first always have to find, we need to find all critical values. Okay, because the critical values are, kind of narrow down where our maximum or minimum can possibly happen. Because local maximum and minimum values can only happen among the critical values. Okay, so we have to find all critical values. But then once we've had that point nailed down, then the big step 2 right here is to, okay, so we're going to have to decide, or we're going to have to test. Okay, test if each critical value is a maximum or minimum, okay, or even neither. This is something we can do, okay. And then after that, we're going to calculate, right? We are going to calculate values of the maximum, okay, of the minimum, and also including the endpoints, and also all the 2 endpoints on the left and on the right. Okay. To find absolute maximum and absolute minimum. Okay, so those 3 major steps right there. So those steps right here is what I'm aiming at right here. So this test right here, sometimes the first derivative test works better, and sometimes if the second derivative exists, second derivative can be a lot more effective in this case right here, because we can bypass the lengthy process of building sign chart and check like that. So that's this step right here is where you have, or basically my other points of saying is you have a choice between using first derivative test or second derivative test. Right in this step where you are testing among your critical values, who among your critical value is a local maximum and who among your critical value is a local minimum, or neither. Okay. And now I am going to have another different kind of examples. So it has really nothing to do with maximum and minimum value, but it prepares you for the other kind of problem. So now let's look at example 2 right here. Okay. There are other kinds of applications out there that need to know this information. So I'm going to start out in example 2 by saying we're going to have a function f of x equals how about x to the 4th minus 4x cubed plus 10. Okay. And now we want to find question A right here, part A of our example. We want to find the inflection points, okay, of the function, this function f of x. And so now to find the inflection points of this function, then recall again from our earlier generalization that we wrote down. I already had it erased on the board here, so you're probably going to need to roll back on the video here. But the only way to get access to inflection point is we have to get the second derivative. So first derivative for our function here is 4x cubed minus 12x squared. Okay, but now I'm going to need to get all the way to f double prime. Okay, so f double prime is going to be the derivative of my first derivative, which gives me 12x squared is the first term, but minus 24x. Okay, so now that is my my second derivative. So inflection point, recall from your understanding from your very earlier understanding right here, but inflection point is where we have f double prime at the point, or I was using c earlier, must equal to 0. F double prime equals 0 when we have inflection point. That's just a brief recall of what we've learned. And so in that way, I am going to directly utilize this understanding and bring that right into our problem right here. Our f double prime here is 12x squared minus 24x. So that means I am going to produce an equation for myself to solve. 12x squared in our case here is the double prime is the second derivative of our function, minus 24x equals 0. It's a quadratic. You got quite a number of ways to solve. Okay, I'm more comfortable with factoring out, so I'll go with the next step here is going to factor out a 12x. So I have a 12x here I can factor out, and the factoring here is easy enough. So I recommend doing the factoring for this particular equation here. So x minus 2 equals 0. Okay, so now we're going to solve for two solutions. So this equation produced two solutions for us. X equals 0 is one of them, and x equals 2 is the other one. But now, these are not the inflection points. These are the x values where the inflection points happen on the graph. But we're close. We're very close. Only one step away. The actual inflection point now is that to find the actual inflection points, you have to substitute both of these two values right here, both of these solutions to this equation, into your beginning function to find the actual point, because it's called inflection points. Okay, and so in that way, all right, so now I am going to, for the actual inflection point, now my first solution of that equation earlier was 0. So now I'm going to substitute 0 into the function. So now we're looking at 0 to the 4th power minus 4 times 0 cubed plus 10. So the answer comes out easily 10. Okay, so that's one of them. So that means we have one point right here, 0, 10. We have one inflection point. That's one of it. Okay, and for the other value, I'm now going to substitute in x equals 2 into the function. So f at 2, and that's now we're looking at 2 to the 4th power minus 4 times 2 cubed, okay, plus 10, and that value here can that's a 16 minus a 32, so it's minus 6 right here. Okay, so now we have another inflection point being at 2, negative 16. These are our two inflection points, and that's the answer to the question in part A of our example. Okay, all right, so now let's look at question B of our example. And so now I want to find all intervals of upward and downward concavity. Okay, so as far as concavity, there are always two different kinds. Either you have a cup that's holding water, or you have a cup that's spilling water down. And so we want to find that. And so again, you see, recall from what I have explained earlier. You have a curve that's, see, immediately in this piece of bent shape here I draw, there has to be an inflection point somewhere, because that inflection point is where we switch from one concavity to another. Okay, in other case, I can have a graph like this. Okay, like say, so there's an inflection point right here. We switch from a concave down to a concave up. And so that means that to find all of these intervals of upward and downward concavity, it is best that we already found that it is best that we find these intervals after we have found the inflection point, which we did in this example. And so now I am going to use the sign chart again. All right, so here's on my sign chart. Imagine we have a line of numbers. So I'm going to put my two x values, not the critical values. So it's at this point maybe some viewers are easy to confuse with the critical values, but the sign chart on its own is just a way to check for signs of any expression. 0 and 2. These are the two values that we have found for our critical points. I mean, inflection points, not the critical points. These are our inflection points, the x values of our inflection points right here. And so the sign chart is just the sign chart. What matters now is that I am going to check for the sign of our f double prime right here. And so for this sign chart, I am not going to check for the sign of f prime. I'm checking for the sign of f double prime simply because f double prime is what decides about our concavity, either upward or either downward right here. Okay, and just like the same idea of using a sign chart that we have seen earlier when we were using first derivative test, then this, because we have two values responsible for inflection points, then we're gonna, once we put that on the line right here, then it's going to break the whole line of values into three separate intervals. So this interval here is for those x values less than 0. This interval in the middle is for 0 to anywhere between 0 and 2. And this is for greater than 2. All right, so now I am going and recall again that our f double prime was found to be 12x squared minus 24x. Okay, and so now I am going to substitute in x, pick a value. I'm going to pick a value x equals, how about -1 here. Okay, and because -1 is clearly in this interval, so I am going to substitute -1 into our f double prime. Okay, f double prime, and that gives me, so 12 times -1 all squared minus 24 times -1. All right, so now that gives me a positive, okay, 36. what it means now is that the sign of our second derivative, of our double derivative, is positive sign in this interval over here. So now the bottom row is the row again to show the conclusion regarding the behavior of our actual original function. And so in this interval, our second derivative is carrying a positive sign. That means our function has to have upward concavity. Okay, so that's one interval. And now for the other interval, the same second derivative, but in this interval, let's say I am going to pick, how about I'm going to choose x equals 1, for example. Okay, so x equals 1 is clearly inside of this interval. And now I'm going to substitute 1 into our second derivative, and that gives me 12 times 1 all squared minus 24 times 1. Okay, and so now that gives me a negative, okay, negative 12 like that. Okay, so being the value here, being 12 for the value, that's not what is important, but this sign right here is important. So it tells me that in this interval, my second derivative is a negative sign right there. And that means for our function, the shape of our function in that interval has to be a downward concavity. It has to have a downward concavity. Okay, and in the last interval, right here, I am going to choose, how about x equals 3. And now I'm going to substitute 3 into my second derivative. And here, this is what I get right here. So 12 times 3 squared minus 24 times 3. Okay, and let me quickly step away for a calculation, and I'll be back with the our final answer here for that. Our calculation for this is a positive 36. Okay, so we're back to having a positive sign for our second derivative in this interval. So that means the function itself will be concave up. We'll have the upward concavity in that interval. All right, and so now we have enough information to make our final conclusion here. So let me now get back to my other board. So for this part B of our example, concluding out, then we're looking at for upward concavity. We're having that in two intervals. One of them is anywhere from minus infinity, anywhere between minus infinity and 0, and then or in another interval anywhere between 2 and positive infinity. So we found two intervals for upward concavity. And for downward concavity, okay, down concavity, allow me to write that in short right there, okay, shorthand writing. Then we're looking at that only interval here is between x values between 0 and 2. Okay, and that's our interval for downward concavity. All right, so before we are completely finished with this lesson right here, let me quickly show you the graph on our example 2 right here. So now allow me to put the graph in a little bit off scale right here. But this is the graph for our function f of x equals x to the 4th minus 4x cubed plus 10 right here. Okay, so we found through the math that, and in our work that I've shown on the board, that x equals 0. So there's one of our inflection points right here. So in part A, we found the inflection points. One of them is at 0, 10, and the other inflection point we found was right here with coordinate 2, comma, negative 6. Okay, and so that was the inflection point. So now in part B, I was looking at those intervals for concave up and concave down. So let's have a look, or let's have a closer look in here to see how the graph is consistent with our results we have done on the board there. But so the interval anywhere from negative infinity, the interval between negative infinity and 2 was the interval where, according to our calculation, it was a concave up interval. So look at the shape of the graph right here. So this piece right here is the piece where the graph appears to be coming out from a cup that's pointing up, that's holding water. So obviously this is concave up right here. The shape of this piece of the graph from here in here, right, is a concaving up concavity. And then this other piece in between the interval from 0 to 2 is apparently pointing downward and in a bent down shape. So in that way, that's how we saw in our conclusion earlier that it was a concaving, it was a downward concavity for our shape of the graph in this interval, anywhere between 0 and 2. And further, we had another interval anywhere between 2 and positive infinity. So you can see that this is almost like a complete full cup right here, pointing up and holding water here. Okay, so it's concave up again for the interval anywhere between 2 and positive infinity. And that is how it was agreeing with the work we have done on the board earlier.